Welcome to video 60 in our series on tensor calculus. In this video, we're going to introduce the shift tensor, which is an object that is new and unique to submanifolds. As the name implies, the shift tensor will give us a convenient way of shifting back and forth between the surface and ambient perspectives. You know from video 58 that we can express our position vector as a function of our surface coordinates s. But of course, we can also express it as a function of our ambient coordinate z, and z with parametric equations is also a function of s. So we're able to construct this composite function. And of course, by now you know exactly what we're going to do. We're going to take the partial derivative of both sides, and we'll start with the partial of r with respect to s on this side. And because s is a surface coordinate, there's only two of them, so I have to use a Greek letter here. On the right side, we'll use the chain rule. We'll start with the partial derivative of r with respect to z. But z is an ambient coordinate, so I need an ambient index. We'll use I and complete it with the partial of zi with respect to s alpha. Again, alpha because there are only two coordinates of s. Okay, so make sure you see the structure of this. The free index in our expression is alpha, and that means that there are two expressions going this way, but the dummy index is I, which is an ambient coordinate, which means that there are going to be three terms on the right-hand side. So we've got an expression that is two expressions with three terms on the right-hand side. Okay, I hope you see as well that this term right here is the expression we derived in video 58 for the surface covariant basis vector. And of course this one is what we've been using many videos ago as the ambient covariant basis vector. So those are known objects. What's new here is this guy. And this is the new object we're going to talk about today, and it's known as the shift tensor. Now the shift tensor is unlike anything we've seen before because it's a tensor that combines the use of a surface index and an ambient index like this. So if you look at it, for each of the two values of alpha, there can be three values of I. So there are a total of 6 components to this tensor. If we were going to express it as a matrix, it would not be a square matrix. It's a matrix that would have 3 rows and 2 columns. Now, you'll see in a lot of literature that authors sometimes refer to this as a mixed tensor. Now, we've said a mixed tensor is one that has indexes in the top and the bottom, but some authors prefer to reserve that definition for this kind of an expression because it mixes the type of indexes to be used together in one expression. And I think there's a lot of merit in that. So we can refer to this as a mixed tensor for that reason. Okay, well, given this definition, we can now rewrite our expression here. We know that the first term is simply our surface covariant basis vector. And then we'll write the shift tensor next, which is just zi alpha, and follow it with this last term, which is our ambient covariant basis vector, like this. Okay, and we said this thing is a tensor, so how do we know that? Well, we know that by the quotient theorem. We know, first of all, that this is a vector, which is a tensor. This is a vector, which is a tensor. We know this is not equal to 0, so that leads us to know for sure that this remaining factor is a tensor. So by the quotient theorem, our shift tensor is indeed a tensor. But to drive that point home, let's go over and derive the transformation rule for this object. Here we have the ambient coordinate zi expressed as a function of s. So if we're going to transform to the z prime system, we need a composite function that looks like this. we'll have zi is a function of z prime. But if we're also going to transform to the S prime system, then we need to have z prime as a function of S prime, and then S prime as a function of S. So this is the full composite function that we need for the transforming both z and s to their prime counterparts. Okay, so let's take the partial derivative. We've got the partial of zi with respect to s, and we need a Greek letter here, so we'll use alpha. And that's going to be equal, first of all, to the partial of zi with respect to our z prime system, so that's going to be with respect to zi prime. And then we're going to have partial of zi prime with respect to s alpha prime. And finally, the partial of s alpha prime with respect to s alpha. Okay, so that completes the chain rule differentiation. So what do we have? Let's clean this up a little bit. This term on the left here is nothing but our shift tensor that we defined a few minutes ago. So this is zi alpha. On the right-hand side, let's pick on this middle term first. This is just what the shift tensor would look like if it's expressed in our prime coordinates. So this is just zi prime alpha prime. Now the first factor then is recognizable as our Jacobian. This is the Jacobian that we defined for our ambient coordinates, j, I prime. And this last factor is also the Jacobian, but it's the Jacobian as defined in our surface coordinates. So this is alpha prime alpha. Okay, you can see right away that this proves that our shift tensor is in fact a tensor. We've got a dummy index here and here, and a free index that matches back here. And we've got a dummy index here and here, and a free index that matches back here. So that's the classic form that we need to prove that our object is a tensor. Alright, we do need to notice that there's one additional thing we need to include in this form, and that is, of course, we already know that we have to have a Jacobian factor for each index, but we also need a Jacobian factor that matches the form of the index. In other words, for an ambient index like this, we need it to match an ambient Jacobian factor like this. This term, j, I prime, will have 9 components because I and I prime can each be 1, 2, or 3. But the alpha prime index matching this one matches a Jacobian that has only 4 components because alpha and alpha prime can only be 1 or 2. Alright, but in any case, we have proven that we have a tensor here. Alright, so since we know we have a tensor, let's lower the ambient index here. And we lower an index by contraction with one of our metric tensors. So we will contract this with our ambient covariant tensor. When we do this, that lowers this index into the first position, and it becomes zj alpha. Okay, now let's take this and raise the alpha index. So we'll have j alpha, and to raise this surface index, we need to contract it with a surface contravariant metric tensor, such as S alpha beta. Alright, so the effect there is that it will raise alpha to the upper position. And according to our syntax, we'll need to put a dot here, beta and j. But the dot is there to remove the ambiguity about the indexes so that we can keep the indexes straight. But in this case, we have no trouble keeping them straight because beta is obviously a surface index and J is obviously an ambient index. So it's okay here just to express this as Z beta J. So what we've done is to simultaneously lower the I index and raise the alpha index to get this form, and I call this the inverse of our shift tensor. And of course we could have done this whole thing in one operation, just making it a double contraction. So let me write that down, and I'll also rename the indexes at the same time. So we'd have Z alpha I would be equal to Zij contracted with S alpha beta contracted with our shift tensor Zj beta. So this one expression right here will simultaneously lower the I index and raise the alpha index. Okay, now notice that if we were to express the shift tensor as a matrix, it's going to be a matrix that has 3 rows and 2 columns. But our inverse is going to be a matrix that has 2 rows and 3 columns. But either way, each of these objects have a total of 6 components. Okay, with that, let's return back to our main line of investigation. So now that we know we're working with a tensor, then this of course is a tensor equation. And as with any tensor equation, we can flip the position of all the indexes. This expression leads automatically to this one, where we have the contravariant surface basis vector equal to our inverse of our shift tensor, Z alpha I this time, times the ambient contravariant basis vector, like this. So this is something we can always do with any tensor equation. So now what I want to do is to find the dot product of the contravariant basis vector and the covariant basis vector, like this. Okay, so the first term here, S alpha, we'll just use this expression. It's going to be our inverted shift tensor, Z alpha I times Zi. And we're going to dot that with S beta using this form of here. So our shift tensor here will have beta, and I can't use I, I've got to use a different letter here, and we'll contract that with Zj like that. Okay, now on the right hand side, the dot product of Zi and Zj, of course, gives us just the delta function. So these two collapse into a delta function. We're left with the two shift tensor terms here, Z alpha I and Zj beta, and the dot product of the two basis vectors here just gives us a delta ij. Alright, so where that leads us is this. On the left side, we know that this dot product is going to give us delta alpha beta. And on the right-hand side, our delta function over here is going to absorb the j index. And so that's going to leave us with these two terms. We'll have Z alpha I times Z I beta, because this j got absorbed and replaced with I here. So that leaves us with this very important relationship. And it is that the contraction between the shift tensor and its inverse contracted with the ambient index is going to give us the Kronecker delta. Now it's important to understand that this is only true if we contract the ambient index. This will not work if you contract the surface indexes. That contraction leads to a totally different result and is something we'll explore in a future video, but it's never going to give us the delta function. It'll give us the delta function only if we contract along the ambient index like this. Let's now consider a vector t, and we'll stipulate in advance that our vector lies in the tangent plane. So if it lies in the tangent plane, we can express it as a linear combination using our surface basis vector. So we can express it this way: T alpha contracted with our basis vector S alpha, like this. Okay, but we can now replace S alpha with its equivalent in the ambient space by using our shift tensor. So this would also be equal to T alpha times Z I alpha contracted with our ambient basis vector Zi. So don't miss this. I've simply replaced this with its equivalent here according to our definition of the shift tensor. Okay, now that tells us in turn that not only can I express T as a linear combination using our surface basis, but I can express it as a linear combination using our ambient basis. In other words, this pair of terms right here will define the scalar value, that is the vector component, as it is needed to combine with the ambient basis vector to produce the linear combination. In other words, we can say that this is equal to Ti times Zi. And that means that we really can now equate this expression to this one. And that's what I'll do in the next line here. We'll simply say that Ti then is equal to Zi alpha times T alpha. So the shift tensor contracted with the vector components in the surface perspective will give us the vector components in the ambient perspective. Okay, now let's multiply both sides of this by the inverse of the shift tensor. So we'd have Ti times Z with I down here this time, and I can't use alpha, I've got to use a new letter beta, and we'll multiply this by the other side as well. So Zi alpha T alpha times Z beta I. All right, now compare this factor and this one with this expression right up here. And you can see that we have a contraction of the ambient index here. So these two terms together are going to produce this delta function. So we will replace them. We will have T alpha, and then the other two terms together will produce delta beta alpha. And of course, this absorbs the alpha index, giving us T beta. And now I can swap sides of the equation and rename beta back to alpha, and that'll give us T alpha is equal to Z alpha I times Ti. So this equation is one in which we can start with the vector component in the ambient perspective using the inverse of our shift tensor, and that'll produce the vector components in our surface perspective. So I'm sure at this point that you can begin to appreciate why we call this thing the shift tensor. It gives us the ability to shift from the surface perspective here to the ambient perspective, or from the ambient perspective to the surface perspective. But don't miss the fact that all of this, however, is predicated on the fact that this vector lies in the tangent plane. We'll deal with the more general case in a future video. All right, I expect by this point you've probably begun to develop a brain cramp, so let's wind the video down by doing a recap of everything we've accomplished here. The first thing we did was to define the shift tensor as the partial derivative of our ambient coordinates with respect to the surface coordinates. And in the process, we wind up with what we can appropriately refer to as a mixed tensor, because the tensor has both ambient indexes and surface indexes. Now note that as a matrix, this form would not be a square matrix. It's a matrix that would have 3 rows and 2 columns. So it has a total of 6 components. Alright, from there we went on to derive a transformation rule that looks like this. And notice that we have a dummy index here with a free index there, a dummy index here with a free index there. And therefore this form meets the qualifications for the transformation of a tensor. We simply have to have a Jacobian factor that is associated with each of the indexes, and the Jacobian factor, of course, will be the type that matches the type of index. And if it does, then that proves that we have a tensor. Okay, the next thing we did was to show that we can simultaneously lower the ambient index and raise the surface index to invert the form of the shift tensor. So we lower the ambient index by including this factor, we raise the surface index by including this factor, and these two operations together will invert the relationship of our shift tensor. The next thing we did was to show that if we form a contraction of these two forms, this one with this one, we're going to get a delta function. So we're contracting along the ambient index. It's important to remember that this only works when we contract the ambient index. It does not work when we contract the surface index. All right, with that, we're finally able to derive each of the following relationships. We see that we can shift from the ambient basis to the surface basis. We see that we can shift the vector components from surface components to ambient components, or we can shift the ambient components to surface components. And of course, all of these being tensor equations, each of these forms will work. Okay, and so with that, you can finally appreciate why we refer to this as the shift tensor. It gives us the means to shift back and forth from the perspective of the ambient coordinate system to the surface coordinate system. In the next video, I'll show you how all of this applies specifically to each of our sample surfaces.